Hello all, and welcome to this overview of CSD3084, Acoustics and Speech Science. So provide a hopefully relatively short big picture of what we're going to be doing in the course this semester. Everything that we do in the class is going to be in the context of the idea of the speech chain, the set of processes that happen in spoken language communication between the speaker and the hearer. We're going to talk a lot about different tools that get used under the guise of speech science to look at the acoustics of speech and how it's articulated. And we'll touch a little bit on applications of speech science to various areas of speech disorders in the field. So the idea of the speech chain is that speech starts out in your brain as some message you want to convey, some content you want to get from your head into somebody else's. We encode that speech as an acoustic signal by moving our articulators around. That acoustic signal propagates through the air where it eventually is received by a listener, causing things to happen in their ear. Information about that acoustic signal, like frequency, periodicity, and intensity, is extracted, and this information gets basically turned back into speech as it gets decoded in the brain of the listener. Here's one image of the speech chain from a book on speech production, which again has speech starting out in the speaker on the left in the brain, information coming from the brain, moving vocal muscles around, the movement of those vocal muscles creating sound waves, those sound waves running into someone's ear, and then again through neurological processing going into the brain to come back as the message to be communicated. The speech chain can be talked about in a variety of ways in terms of anatomical location, from information in the brain to things happening in the mouth to things propagating through the air to things happening to the ear, which then turn back into activity in the brain. We can talk about the type of information that's being talked about. Linguistic information in the brain, physiological information having to do with how the mouth moves around, acoustic information in how sound propagates through the air, physiological information again as the ear gets affected, and turning that back into linguistic information that hopefully matches the first linguistic information that the speaker was trying to convey. There are terms for the different processes involved in these different steps in the speech chain, from the generation of a message to the articulation of a set of speech sounds, to transmission through a medium, in this case sound traveling through the air is the thing we talk about the most in speech science. Reception of that signal as perception by the listener, and then turning that perceived information into a message that you understand in the process of comprehension. And then last but not least, the type of information that's involved at each stage. We start out with something abstract, something symbolic in the brain, a set of words or sentences that we want to produce that represent concepts. That becomes a set of gestures as part of speech production. That becomes a sound pressure wave as part of acoustic transmission. That sound pressure wave gets broken down into frequency and intensity components in the ear. We will have a tool that we can use to visualize speech called a spectrogram that basically captures that representation. And then that frequency and intensity information gets turned back into symbolic information, a set of speech sounds, which make up a set of morphemes, which make up a set of words, which make up a set of sentences, which have a particular meaning. Speech science covers primarily the middle part of this speech chain. We're going to take speech articulation, aspects of acoustics involved in transmission, and aspects of perceptual physiology in the ear as the focus of study for this class. A basic overview of speech production involves movements of the articulators at a pretty high rate. We generally produce 2 to 3 syllables per second when we're speaking. Each syllable contains 7 to 11 different combinations of a place where something is articulated, a manner of articulation like a stop consonant or a fricative consonant or a vowel, and the presence of voicing, phonation, or not for each of these speech sounds. These movements are done by motor commands. Each articulator is moved around by multiple muscles, and those muscles need to be coordinated to make speech happen. Sometimes there's conflicts in what those muscles need to do, resulting in modifications of the speech that's produced due to co-articulation. In terms of acoustics, we'll get into basically the description from physics of speech sounds in terms of periodicity, whether they have a repeating component to them, in terms of duration, how long they last, in terms of their component frequencies, so kind of like breaking light down by a prism into a rainbow. We can break speech down into a set of higher and lower component frequencies, and then intensity of that speech, how loud the acoustic waves are. We're going to take information that you mostly learned already about articulation from anatomy and phonetics and talk about how that articulation results in the acoustics that we get from speech, and then also talk a little bit about how some of those bigger pieces of speech, like the intonation across a sentence, gets encoded in speech sounds. Here's an example of one of the tools that we use in speech science to look at speech. At the top of this image, there is something called a waveform, which is basically a recording of the sound pressure at a microphone, usually on a computer, across time. The bottom part of this image shows that same acoustic information across time, but it's been broken down into the lower and higher frequency components, which more or less gives you a visual picture of the information that's extracted from speech by the ear. So as I said, the ear processes speech, pulls out frequency information. There's also an aspect of perceptual processing that dynamically adjusts how we listen to speech on the basis of the context that we're hearing the speech in. From that frequency information, we extract information about the phonemes and suprasegmental components of the speech. So categorizing our different phonemes or phones together, considering that acoustic information in terms of the text that's being conveyed, the context or situation in which that's happening, and who the talker is, which affects what frequency information we expect. Speech science gets applied in speech pathology and audiology to a variety of disorders, such as voice disorders that affect phonation, neurological speech disorders that affect articulation, craniofacial speech disorders that affect the structures that get used in speech, hearing impairment where the reception of speech information can be affected, and where we can try to adjust for that effect through something like a hearing aid. Speech science is also applied to accent reduction, a case where a person has particular goals for what they want their speech to be like, for it to be clearer, for it to be closer to what's considered the standard production of language for different social situations. By using the tools of speech science, we can look at how the person articulates their speech and the acoustic result, and give them feedback about how to modify the way they produce speech to better match the standard they desire. We're going to talk a fair amount about instrumentation in this class. The primary thing we will do is acoustic analysis, because you can pretty much do it on any computer these days. There are other specialized tools for speech science that look at airflow out of the mouth or nose, that measure physiological things electrically, either in the brain or in the muscles. In the anatomy class, you probably heard a little bit about video stroboscopy, looking at the vocal folds vibrating in speech. There are also a variety of commonly used clinical tests of speech production and speech perception that could be considered instrumentation in the field as well. I've provided a link here for some examples of these things that if you took the anatomy class with me, you may have looked at a little bit before. These are recordings of words exemplifying different speech sounds in English, with a video of the lips moving, an ultrasound of the tongue moving, and a nasoendoscopy giving you a view of the larynx to give you some idea of phonation happening. Those videos have a structure sort of like this, where there's a lip video showing what the lip is happening. An ultrasound is the main thing, showing you what's going on with the tongue. In this case, the tongue tip is toward the lips, as you would expect, and the root of the tongue is toward the larynx. And then a video giving you a view of the larynx. In this particular case, this is what things would look like for something like an O high back rounded vowel, where the video shows the lips rounded, the tongue body is pulled posteriorly and raised, and the vocal folds are together to produce phonation. Acoustic analysis has been used extensively in computer applications, so to do things like speech synthesis. Acoustic information is stitched together to create novel stretches of speech on the fly. Acoustic analysis is also used in automatic speech recognition. If you talk to your phone to give it commands or to have it write out a text message for you, automatic speech recognition is analyzing the acoustics of that speech to figure out what you're saying. These tools are sometimes used in CSD, so there are more and more pieces of software that get used for speech therapy or for accent reduction training, where the computer has an acoustic target for what it wants the person to produce, and the person can practice that production, getting an idea of how close they are to the desirable production. This acoustic analysis is also used in programmable hearing aids and cochlear implants. So, for example, hearing aids don't just take all the sound and make it louder. It selectively makes sound louder to adjust for the hearing loss that the person has, and also potentially to focus on what's likely to be speech information and leave out what's likely to be background noise. Similarly, things like voice identification for security, or talker identification for forensic science, which is science applied to criminology, are other ways that acoustic analysis have been used in applications in CSD and beyond. I'll probably talk about these various applications as we do the detailed bits in the class, but they won't be a big focus. Our primary focus is going to be on all the different speech sounds of English, how they're articulated, and what their expected acoustic results are.